Okay, so this lesson is all about what is a renewable resource and a non-renewable resource. So last lesson we talked about what these resources were and what humanity needs to survive. We talked about water, soil, energy and the mining process in detail. And we looked at some of the environmental impacts of mining. We also looked at this concept of a circular economy where there's as minimal wastage as possible. Now we're going to discuss what is a renewable resource, how are timescales really important in defining renewable resources, and when and where do different energy types have the greatest potential use. So we'll be going through a number of different energy sources today, some really cool ones, mostly renewable energy because we talked a little bit about coal power plants last lesson. And we're going to discuss in what context they can be used because you can't just put them anywhere. They have to have the specific resource that you're looking at. If you're doing solar, you need sun, obviously. So these are the questions I want you to have in mind that you should be able to answer by the end of this lesson. So what if we had unlimited energy? I hope you recognize this. This is Tony Stark in Iron Man, and this is his reactor. It's the arc reactor. It's the one that is the prototype for the thing in his chest that keeps his Iron Man suits running all the time. But we have this question of what would happen if we had unlimited energy, because that's what he's built. He's built an unlimited energy device. And it would probably transform the way we live our lives quite significantly. And the reason I ask this is because we're actually building these. This is the facility that houses ITER. I actually don't know what the acronym stands for. Something. It's a fusion reactor. This whole area. Houses all the machinery and things you'll need, and then there's one very big 7-story building in the center where the actual fusion reaction occurs. This is a diagram of the outside of that 7-story building, so you can see each level has different components running through it. It is a highly complicated machine. Some people think that this is the most complicated machine ever built. This is where the actual fusion reaction will take place. It's actually not that big itself. It's tens of meters across or something like that. You can stand up inside it. It was started being built in about 2020. It's going to do its first test run in 2025, and the full fusion reaction should begin in 2035. Its initial budget was about 6 billion euros, and it's now projected to be about 22 billion euros, but some think it's closer to about 65 billion. It's kind of getting expensive. There's about 44 countries involved in this project. And it's a very, very highly complicated engineering project, probably the most ambitious collaboration since the International Space Station and the Large Hadron Collider, which is the big particle collider, CERN, if you know it. So basically what happens in here is you get the fusion reaction, which fusion just means you get two atoms being hit together, and they create a new molecule where a new atom, where their nucleuses get bonded. If you don't know what a nucleus is yet, don't worry. We'll do that when we do chemistry later in the year. But this reaction, as simple as it sounds, can only happen with the heat of the sun. So you need, in the center of the sun, you get temperatures of about 50,000 degrees Celsius. At the surface, it's about 6,000 degrees Celsius. So it's very hot. And basically you need some very fancy magnets around the outside to make sure that hot fusion, hot plasma inside doesn't actually touch anything. It needs to be kind of suspended in midair by magnets. It's pretty cool technology. This is the first reactor that should be actually producing power. So it takes it has its own power grid to actually get it started, because obviously it needs a lot to get it started. And once it gets started, it should be able to create its own fuel, tritium. The reaction itself will emit things that will create a chemical called tritium, and that tritium will go back into running it. So it kind of creates its own little circular process, which is quite cool. So what is a renewable resource? Well, it's a bit of an interesting definition. I want you to think about if you know what a renewable resource might be. Have a guess. Well, if you've had to think about it, a renewable resource is essentially something that can be replenished within a human lifetime. And why do I say within a human lifetime? Well, groundwater takes a long time to be replenished. If you use the groundwater, you can have water for entire cities. India uses a lot of groundwater. But it doesn't last forever. You need rainfall or glaciers to melt, and India has the Himalayas nearby, so they've always had a lot of snow melt, but there's not a lot of snow anymore in the Himalayas because of climate change. So they're not really getting any snow melt going into their groundwater, so they're using their groundwater much quicker than it can be replenished. So it's not a renewable resource, even though water tends to be a renewable resource. So it has to be within a human lifetime. Okay, that's very important. Write that down. So the water cycle is why we consider water a renewable resource most of the time. You know, the oceans, you get evaporation from the oceans, it condenses into clouds, and those clouds precipitate back down as snow or rain into our rivers and into our lakes and then back out to the ocean. It is a cycle. The water doesn't go anywhere. You can't take water and throw it off the planet. It is a closed cycle. And hopefully you're in the lab right now and you can look up to the front of the lab. There's a big jar with a plant in it. That jar has been closed for close to, when were those kids in year 10? About 5 years now. It's never been opened. All the water that's in there was the water that was added when it was originally there. It's a little bit too damp. It always has been, that particular one. So a lot of the plants died off. There's only a couple of different plants living in there now, whereas originally there was about 4. But what happens is it gets the sunlight it needs, and all the water gets recycled again and again and again. It has never been watered, that particular jar. So that's the same as the planet. We are in one big jar. The water just gets cycled over and over again. Another renewable resource is considered hydroelectric power. You need a large river system for this to be profitable or viable. And you also need somewhere that you can build a dam, somewhere that's not going to destroy like any endangered species or anything like that, because dams do destroy river ecosystems near where they're built. And you need to be able to then flow that water through the dam to create this hydroelectricity. So you need a large river and somewhere you can build a dam. You also, so how it works is the water flows downhill just because of gravity, and there's a turbine that spins, and there's a generator. We talked about this last lesson. It's filled with magnets. The magnets then rotate and push the electrons in anything has electrons, any metal has electrons that flow, and then they flow out to our electricity grid, to your power points. So pretty much any power station, be it hydroelectric, coal, whatever, they all use this process of turbine and generator that I know of. Pretty much everything. Geothermal, if you know that, is the same. There's also something called pump storage hydro. That's essentially where you pump the water back up when you've got excess energy. So if you use 100% renewable energy, you use solar panels or wind turbines, right? I'm not good at drawing, yeah. But, and you use these to power the generator in the opposite direction. It spins the turbine and sucks the water back uphill now rather than downhill. That allows you to have more water in your dam to be used later during when you don't have as much renewable energy being produced. This is pretty much the one of the only viable technologies that could make us 100% renewable, because you need what's called a baseline load of power. You need power all the time, right? Not just when the sun's shining or the wind is blowing. It doesn't work. So hydroelectricity and these dams where you can pump it back uphill, it's called I've got it on the next page, pumped storage hydro. That is the only way to really store huge amounts of power that we know of. Batteries don't store enough power for entire cities. So a study by ANU, if you look at this, if you downloaded this PowerPoint, in the notes section, you've got the link there if you want to read about this. It found 22,000 sites for pumped storage hydro in Australia. We have about 15 or 20, I think, in the country so far, but and new ones underway. But we could have a lot more if we wanted to. We really can go 100% renewable if we so choose, because we've got plenty of wind and solar. There's also this really cool form of energy called tidal. So this is actually submerged in the ocean, and as the tides go through, they actually spin this big turbine. So rather than heating steam into a turbine through a coal power plant, rather than burning it, you just have this turbine that's straight using the water. This one sits about 35 meters below sea level. It's about 16 meters in diameter, and produces about 1 megawatt of electricity, which is not much. In contrast to a hydroelectric dam, we've got the Gordon Hydro Dam, which is the biggest in Australia, that's in Tasmania, that produces 432 megawatts of electricity, which is about 350,000 homes. Just to give you like a context of how much power these are producing. Certainly you can't even power a city with the biggest hydro dam that we have in Australia. We actually have cable between Tasmania and Australia that actually transmits power when we need it to. I forgot what the name of it is. But yeah, there's a cable running under the ocean the whole way. You have got, this is a map that shows you where the tides are greatest. So not everywhere is good for tidal power. There's great tides up in the northwest of Australia, like huge tides. They drop up and down like 10 meters every tide. So really great tidal power up there. Not great if you're anchoring your boat, because you anchor your boat and then you end up on the ground and your boat's tipped over and all your things have fallen out of your cupboards. But it's great if you want to create tidal power. You can also do wave power. This is a type of wave roller technology, and that produces the same as the tidal power one, so about 1 megawatt. But you can have lots of these, right, in the ocean going back and forth all the time. So you can have it's like a farm of them, similar to like wind turbine farms. You can have wave power farms. They're pretty hard to run though. Seawater, salt water, is really hard on mechanical components. So that's why these technologies have been a little bit slower to develop. And this kind of shows where the waves are the best in the world. So we actually have good waves down here. We don't have great tides in Melbourne, but we do have great waves. So you can see anywhere up here, you'll have bigger wave power if you want to put them there. So there's certain areas that have a predisposition to certain types of electricity. For wave power, you can see it tends to be the really high latitudes. So high latitudes, whereas the equatorial regions don't have a strong wave. So that's just because the winds are higher in the high latitudes as it gets colder. Whereas with tidal, it's wherever the moon, it's to do with the shape of the oceans and the way that the moon pulls on the water in different areas. It just collects. So New Zealand is a good spot. Northwestern Australia is a good spot. There's a good spot in the Americas here, between the Americas, South and North America. It's a good spot up near Alaska. There's a good spot around Europe here. So United Kingdom has great tides for it, and so on and so forth. There's also this really cool type of power called geothermal, which is basically where you just pump water down. It heats up from the earth and then it creates steam going out. So very easy, simple technology. You just have to dig down deep enough. Some areas of the planet are better for this than other, because some areas of the planet have less crust. So you get this has like the aquifer temperature. So this is the underground groundwater, and that gives you an indication of where there is better heat for geothermal. So you just kind of pump up the groundwater in these areas. So you can see there's large areas in central Australia where this is a viable source of power, and little pockets all over the world. And they're relatively cheap and easy to build. But because they haven't been done so much, that's why they're kind of still a little bit more expensive. But as the technology becomes more common, it becomes cheaper as well. So basically, it's wherever the crust is thin, the Earth's crust. The Earth has a crust, and beneath it is the mantle, where it's molten rock. And if the crust is thin enough, you get close enough to that really hot center of the planet. Okay, wind power. A wind farm with hundreds of these things, produce about somewhere between 500 megawatt to the biggest one is around 1200 megawatt. So bigger than the biggest hydro. So huge amounts of power. And you can put them in the ocean, you can put them on land, anywhere where there's wind. And you can see that there are some areas which are very good for this around the edge of Tasmania, the coastal areas. Even though you can't see it, there are a lot of places in the coastal areas. The bottom of South America has got hugely high winds. This looks like part of the North Pole sort of region. You've got areas around Alaska and northern US. You can see along these coastlines, even though you can't see it, there's a lot of areas along the coastlines here. Northern Africa, the UK, and Northern Europe. So wherever the wind is highest, looks kind of similar to the wave power, because winds and waves tend to be high together. Solar is great. Solar you can pretty much put anywhere. They're so cheap to build these days that Germany, even though it's really grey and dark, I lived there for a year, they still produce some ridiculously high proportion of their power from solar, because everyone has a solar panel on their roof. I think it might even be government mandated that if you build a house, you have to put a solar panel on these days. And they pay back the money very well. So here we don't really get that much money back for having solar panels and pumping power into the grid, but there they get really good rates because the government has pushed going green, unlike our government. So it's worth putting solar panels on. So this is the biggest solar farm in the world. It's Budla Solar Farm. I don't know if I'm mispronouncing that. Maybe someone can correct me. Solar Park in India. And this produces about 2,245 megawatt. So lots and lots of power across about 14,000 acres. But there's new bigger ones being built all the time. People just build them constantly being built. And you can see that a huge portion of the planet is useful for that. And I was talking about Germany, which is here. They produce huge amounts of solar, so you don't even need to have that much because the solar panels are so cheap. In Australia, it is a joke that we don't have more solar. We do have lots of solar, actually, but we don't. We could have a lot more solar than we do. So why don't we use more renewable energy? Well, that is a very good question. And part of it is to do with how we consume power. So basically your power generation and your power consumption have to be equal, right? They have to be equal. You can't put more power into the electricity grid than you need. So here you basically have the grid. So all of the power lines that you see running along the streets that run to your homes, they are part of the grid. Everything is connected. Everything needs to remain at 240 volts. In summer, because there's so many solar panels on people's roofs, we're getting voltages of up to 251 volts, which is getting dangerously high for the components of our electrical grid. It actually can't handle too much power. And so what's happening is we're having to take coal power plants offline, but then we might actually get power outages when we do that because we don't then have the power when the sun goes behind clouds or when the wind power drops off. So renewable energy sources tend to be unpredictable. And basically all these different power plants, whether you've got nuclear, we don't have any nuclear in Australia, hydroelectric, we've got lots of hydroelectric, not heaps of it in Victoria, but we do have cables to other states. So all of Australia is almost, maybe not all of Australia, the nearby states are all connected by an electrical grid. I don't think we're connected to Western Australia. I think we can connect up to South Australia and New South Wales and Tasmania. But basically we're building up our infrastructure all the time to make the grid bigger and bigger, because what it means is all of these different sources of power, they even out. You can store it in that pump storage hydro that I was talking about before. Or in South Australia, they've got batteries that help when they have short-term power outages. Doesn't help long-term, but if you have short-term power outages, the batteries can really even that out. And you have to somehow deal with this unused power generation. So you have to store it somewhere. So they're all connected at one time. You need to, whatever's going in needs to be coming out of via the houses. So if people had batteries in their homes, they could actually store power for overnight as well. So there's different ways to do this storage. You could have people having batteries in their homes. You could do pumped hydro at a bigger scale. You could do big battery banks like South Australia did. But you have to maintain exactly 240 volts all the time and a certain amperage as well. I think the amps vary, but depending on what sort of transformer you have. So out front of the school, we had our own little box installed to give enough power for a school. And different facilities will have different sort of things. So industrial customers, they will have different power sources to what we have because they need to run different machinery. I think it's pretty interesting. Anything that the power sends out either needs to be stored or used. This is called the load. What's used is called the load. And then you've got the power that's generated and the power that's stored. And this all needs to balance out. In 2016, there were 3 months of blackouts and brownouts in Tasmania. There was an excessive use of hydro capacity by Victoria that left our dams low. Their dams low. So we kept using, this is the cable that runs between us. It meant that all their water ran out of their dams. And then the cable broke to Victoria, meaning that we couldn't then support them back when they had problems. So the cable was cut and took months to repair. About 100 kilometres off the coast of Tasmania, so really in the middle of the ocean. The company was called Basslink, the Bass Strait Basslink. And they said it could operate at 230 megawatts for extended periods of time without overheating, but they were wrong. And it failed, and basically the cable, you can see here, the cable just swelled and broke from the heating that occurred because it had too much power running through it. So the storage, there's many different ways to store power. There's pumped storage, which is where you pump water uphill into an upper reservoir. There is compressed air storage, where you push air. You need to have a cave underground. I know it sounds kind of funny, but that's what it is. You find a cave underground that is fairly airtight, and you pump air into it, and you compress that air just as you would into a little gas canister, and it's the same. You just spin it through a turbine, right, to when it comes out, and then you can get that energy back. But there's only so many places you can get these deep underground caves. I don't know, they might be able to start building them these days, but when I first looked into the technology, you had to have a suitable underground area. You can store it as molten salt. A lot of solar systems, rather than using traditional solar panels, they actually use mirrors to reflect the heat into a container of salt that then melts. Molten salt will stay hot for many days, so you can then use that power station, even though it's a solar power station, runs through the night because the salt stays molten, and that salt can then be used to heat water. You can also use chemical batteries. So these are the four main types of storage, and really the only viable ones at this stage that we know of. And it's a delicate balance, right? We need to balance our generation and consumption. So what are some of the non-renewable resources? Well, we talked about coal. You remember how long it takes? Hundreds of thousands of years. Millions, hundreds of millions of years. So about 400 million years is about the minimum, I think. About 400 million years for it to form. So it's not going to form within our lifetime. Anything that's here can be thought of as all that's left. Soil is a non-renewable resource because it takes 500 years for 1 centimetre. So once it's gone, we're not getting it back. That's why losing soil is really important, and we're losing it at an alarming rate all the time. It's something that doesn't get talked about enough. Uranium-235 is while it has very little of it is used in the power generation process, we could only run for about 200 years. So we don't actually have an unlimited supply for our nuclear power plant, even though most people think nuclear is pretty green because it doesn't have any carbon dioxide output. It is not long-term renewable. I don't know, if you think 200 years is long-term, maybe it is to you, but it has to be within a human lifetime, so it's not replenished, so that is it. So what does the future look like? Nuclear fusion is not limited like nuclear fission. So this is the uranium is limited, whereas nuclear fusion is not really limited. The materials you need are lithium, which is pretty much unlimited, and deuterium, which can be taken from water, which is obviously in the sea. So we've got about 6 million years worth of that before we need to start mining Jupiter, probably, for gases. Solar is also pretty much the future. We need, this is the type I was talking about before. You have the molten salt container up here, and all of the mirrors are just angling towards the molten salt container. You have got a wind power station that's also renewable. That's basically what we need. Nuclear fusion, not nuclear fission, solar, wind, and some way to store it. That's what we need to avert climate change, and we need it as quickly as possible. So whether that happens in time to avert total catastrophe is up to you guys. What is a renewable resource? I hope you can answer that question now. How are the timescales important? It has to be within a human lifetime. When and where do the different energy types have the greatest potential use? So if I said wind, could you tell me where the highest winds are on the planet generally? Could you tell me where the highest waves are on the planet generally? Where are the best tides? Where's the best solar? Towards the equator, you could say. You don't have to say specifically, but it's good if you have specific examples as well. So think through those things, and hopefully this was an interesting lesson where you got to learn about how we power our civilization.